Here's another interesting one. The moment of inertia of a solid cylinder of radius r and length L around an axis through its center perpendicular to the plane of its base. So, solid cylinder. Here's my cylinder, and we're going around this axis that passes through space, and we said the cylinder has length L. Now, one thing that is important to note is that while this cylinder is a three-dimensional shape, the third dimension, this length, doesn't change anything about what's going on, because if you take it in circular slices all the way down, it's exactly the same all the way down, same distance from the axis of rotation. So that third dimension won't add too much complexity to what we're doing, but we do need to deal with it. Now, our dm, we're going to use rho dv in this case because it is three-dimensional, so we need mass, or a volume times density to get a mass. But now this is a little bit trickier. If we were to use Cartesian coordinates, x and y, well, there isn't a consistent relationship. Well, there is a consistent relationship, but it's not very pretty to deal with when you're going on this arc here around a circle. So this integral is much easier to do if we use cylindrical coordinates or polar coordinates, because polar coordinates, our shape is just, a circle is defined by a radius equals something, and so then we don't have to deal with any relationship. Then our r, it can just be r, the radius of that point from our axis of rotation, and then we can integrate dr, integrate up from the center of this circle to the outside, and that will kind of be adding up concentric circles, or concentric cylindrical shells, I guess, as we integrate our way out. So those polar coordinates are going to be the easiest to deal with. So radius r, let's do radius capital R, just to clarify the difference between that and the variable r. So then this volume, well, what are we integrating up? We're adding up little shells like this all the way out, where the thickness of this is going to be dr. We know the area of a circle is pi r squared. If we have a circle within a circle, we're taking the area of the big circle minus the little circle, right? So the area of this right there is going to be, the area of the little ring here is going to be pi larger radius minus smaller radius. Well, the larger radius we can say is going to be our r, but then the inner radius is just a tiny bit smaller than that. It's an infinitesimal bit smaller than that. It's r minus dr. Okay, which looks kind of nasty, because how do you deal with this when you're integrating? But if we FOIL this out, we notice we get an r squared. So we have r squared minus 2r dr plus dr squared. That's just what we get when we FOIL out. Let me zoom in here a little bit. That's what we get when we FOIL out that expression. So let's, why aren't you focusing? Focus, darn you. Hello? Okay. There we go. All right. Now doing this math, you can see r squared cancels out. And then we've got minus negative 2r dr minus dr squared. But remember, what is dr? Dr is an infinitesimally small bit of stuff. So that's really small, but if we square an infinitesimally small thing, we get something that's really, really, really small, And so we can basically say that this dr squared is essentially 0 and ignore it. And we get 2 pi r dr, which is actually interesting because if we unroll this, we get something that's basically a rectangle, because this thickness is infinite. Oh, I need to zoom back out, sorry. If we unroll this shape, we get this little rectangle. This thickness is really small, so the inner radius and the outer radius are only very, very slightly different. So you can essentially get a rectangle when you unroll it. When you unroll it, then the length of this rectangle is just the circumference of the circle, 2 pi r, and the thickness here is dr. 2 pi r times dr gets you that area. So our dm then, now we do need a volume, so the circle has area 2 pi r dr, and then that circle extends all the way through the length of the cylinder, so we multiply that by the length, and we've got a volume. So that is our dm here, rho times 2 pi r dr times L. And we can do our integral. We're doing it in polar coordinates, so we're just going from a radius of 0 to a radius of big R. And the 2 pi rho L are all constants, so those can come outside of our integral, which leaves us with an R times an R squared dr. Excuse me. And rho is mass over volume. Volume of a sphere is pi r squared L. Look at that. L's go bye-bye. Pi's go bye-bye. That's nice. And then our integral, the integral of r cubed is 1 over 4 times r to the 4th. We plug in r, plug in 0. This is just 1/4 r to the 4th. 2 times the 4th gets us a half. Mass is there. R to the 4th over r squared gets us r squared. And that is exactly the formula that you were given the other day for a solid cylinder. And so that's how we deal with moments of inertia. Part of your homework is going to be to work out this problem to derive the moment of inertia of a cylindrical shell. So that's a shape where you have kind of an outer radius and an inner radius, and then it extends in a cylindrical shape, and that hole goes all the way through, kind of like a roll of paper towels would be a cylindrical shell. You can sort of follow the pattern of this one. You'll have to tweak a few things, but you can kind of follow the pattern of this to figure that one out.